Alright, so I'm going to walk you through the example math problems for the study guide. And I have a printout of the page. This box above that we see, this sucker here, this is going to be right on your exam. So you'll have this information. So you just have to be able to pick the right equation and then work the numbers properly. So if you have 6,000 BTUs of heat energy and it's added to 10 pounds of water with a specific heat of 1 BTU pound degree Fahrenheit at the starting temperature of 50 degrees Fahrenheit, what is the final temperature of the water? So I wrote out all the pieces to my problem. I have my mass of 10 pounds, my Q of 6,000 BTUs, my specific heat of 1 BTU pound degree Fahrenheit, and I know my starting temp is 50 degrees Fahrenheit. That'll come in when we do change of temp. The equation I'm going to work with is the change in temperature, which is equal to Q divided by the mass times its specific heat. And now I'm just going to set up the problem. Alright, so I wrote out my problem on my set. I'm going to change colors so that I can cross out things. And when I take a look at my problem, I have the 6,000 BTUs, and that's going to be divided by 10 pounds times the specific heat of 1, crossing out the BTUs and the pounds. And I'm left with degrees Fahrenheit, and I can do this in my head because a nice easy number of 600. And that's degrees Fahrenheit, and that's my final temperature, my final change of temp. Now I have to figure out the final temperature total, because this is just the change. The change is 600 degrees. So if I start at 50 degrees Fahrenheit, I'm going to warm it up by 600 degrees Fahrenheit, meaning the final temperature is 650 degrees Fahrenheit. Final answer. All right, so we'll take a look at the next question. Okay, so question B, a 24 square foot single pane glass door with an R value of 1.54 loses a great amount of heat. How much energy is lost in a 4,500 degree day zone? So I have degree days, which means I'm going to use my degree day equation over here to work my problem. So I wrote out what I need, my R value of 1.54, my area of 24 feet squared, my degree day of 4,500, and the equation I'm going to solve with. Now I'm just going to place everything into the right spot. Alright, so I placed everything into my equation, and I have my R value dividing into 1, and I'm going to cross out feet squared, hours with hours, degrees Fahrenheit with degrees Fahrenheit, and days with days, and I'm going to get BTUs in a year. So I'm going to do 1.54 divided into 1 times 24 times 24 times 4,500, and I get 1683116.88 BTUs per year. Alright, so problem C is an extension onto B. How much energy would I lose if I inserted a 1-inch bubble sheet with an R value of 2.5 over the window in the above question? So everything still exists, and I give you a little hint there. So for question C, I've got two pieces to my window, because if I have my little window frame, it's still going to have the window frame, and then I'm placing a bubble sheet on top. So I'm going to have to sum, that's what the sum symbol is, the two R values together for my 24-foot square area. Alright, so now I have my 1 divided by the 1.54 plus the 2.5, so it's going to be 4.04 divided into 1 times the 24 times the 24 times the 4,500, and units are going to cross out, so feet squared, hours with hours, degrees Fahrenheit and degrees Fahrenheit, days with days, and I'm left with BTUs in years. And this should make sense since I'm adding more layers. Obviously, my number, when I work out my number, should be smaller. I should be losing less energy through my window. And so if the number is bigger than the answer to B, you did something wrong. So it's a good way to check it. And when I plug everything in, I get 4, 6, 1, 5, 8, 4, and that is 0.1, and it's 1.5. I'm going to round up to 6. And that's BTUs for the year. So that's my loss. I look like a G, not a Y, I'm sorry, year on there. All right, taking a look at D. Calculate the total heat transfer for 24 hours through a glass greenhouse with an R value of 2.16 that measures a 980 foot with the heating set at 50 degrees Fahrenheit and the cold outdoor temperature of 35 degrees Fahrenheit. The heat is electric and costs 87 cents per kilowatt hour. How much does the loss of energy cost? So calculating this, we have a time here in the problem, an R value, an area, and a change in temperature. So I know I'm going to use the equation that solves for time with the area and the change in temperature. So let's set that up. So I wrote out everything I need, and so I have my time of 24 hours, my area of 980 feet squared, my R value of 2.16, my change in temperature of 95 degrees minus the 35 degrees, and the kilowatt hours is the next step that we'll do after we find the answer to the problem. I also wrote the equation I'm going to use. I'm going to just plug everything in. Alright, so I wrote out everything. I've got my 1 divided by the 2.16, and that's all times the area of 980 feet squared, and that's times the change in temperature of 95 minus 35, that's 60 degrees Fahrenheit on that. And I'm going to cross out my units of Fahrenheit, feet squared, and I'm going to be left with hours of BTUs. So when I work that part of the problem, I get 2, 7, 2, 2, how many twos? 3 twos, 0.22, and that is hour BTUs, hours of BTUs, BTU. Now the next step is I want to do it for 24 hours, so I'm going to times this by 24 hours. And hours is going to cross out. I'm going to be left with BTUs. And so when I times that, I'm going to have 6, 5, 3, 3, 3, what is there, 4 threes repeating? 3.33 BTUs. Alright, so the last part is to figure out how much this costs in a money amount, and that means I'm going to look up how many kilowatt hours per BTU, and I'm going to divide by 3,413 BTUs per kilowatt hour, and that'll give me my answer in kilowatt hours of 191.42. Yep. Kilowatt hours, and I'm going to do some erasing to make room to do the money amount. But remember, this is the kilowatt hours. Now I'm going to times it by the money amount. So I'm going to take my converted unit of energy loss in kilowatts, and I'm going to times it by the 87 cents, and I get $166.53.9, so it's going to round up to 54 cents. So that's my final answer for question D. All right, question E. When taking a shower, we use 4.5 gallons of hot water with a specific heat of 1 BTU, pound degree Fahrenheit. And the water is heated from 55 degrees Fahrenheit to 112. How much energy is needed to heat the water in transition? Answer in BTUs. So I'm going to be using my equation with the Q. Alright, so I have my mass of 4.5 gallons, and I have to change that to pounds, which is the conversion of 4.5 gallons times 8.3 gallons of pounds. I'll be left with pounds. Gallons and gallons crosses out. Alright, so now that I converted this to pounds, I can plug it all in my equation of 37.35 times 1 pound degree Fahrenheit BNTU times the change in temperature of 112 minus 55, that's 57 degrees Fahrenheit. And pounds, pounds crosses out, and Fahrenheit, Fahrenheit crosses out. My answer will be in BTUs, 2128.95 BTU. Final answer.